Oxygen.
Oxygen's an okay leaving group. It's not as good a leaving group as it's not as good of a leaving group as the halides are, but if I'm telling you predict the elimination products, so I'm telling you it's going to go through an elimination.
Where? H2O is just one of our things that floats around.
We don't care right now.
The hydrogen goes.
Touch it.
So because the hydroxide is acting as a base, if it's an elimination reaction, the hydroxide is acting as a base, not as a nucleophile. So yes, it will still just be floating around as water.
But the hydrogen is what forms the double bond.
Where the hydrogen comes from tells you what product you're going to make. So for this first one, our leaving group is leaving. Our hydroxide can either grab a hydrogen from here or from there. Right, because either way, we're making H2O. And we've got bromide floating around. And then we make two different possible products. We can either make one butene or two butene, which actually has two isomers. So this is a type of stereo isomer that doesn't show up as a chiral carbon. So, and the reason that this happened, if the hydroxide takes the hydrogen from carbon 3, we get one of these two options. If the hydroxide takes a hydrogen from carbon 1, we get the 1-butene. And it's somewhere between us finishing at a slightly different time than I normally do. I don't think we've talked about naming alkenes yet in detail, have we? So in general, alkenes are pretty easy to name. You name them just like an alkane, and then you just specify where the double bond is. And instead of ending as, so this was bromobutane. ENE. So
for naming out
alkenes, which, and remember, alkenes is a double bond between two carbons.
But you specify which one it's on?
Exactly, because if I just said butene, how do you know which of these three is it? It's any of them, right? We don't like nebulous names, ambiguous names.
And then you said for naming them, what did you
We're doing it right now.
Oh, well, I'm trying to write.
So the first thing is the suffix changes. Instead of ane, it's ene. So anytime you see ene, you should be thinking carbon-carbon double bond. And then you just need to specify where that carbon-carbon double bond is, if there's more than one place it can be. So this first example is 1-butene. And the new school way of writing these names actually puts the 1 in between but and ene.
But are we doing that?
Well, because when they
I'll accept either.
when they get super long.
But-1-ene. They mean the same thing. Butene is easier to say than but-1-ene, just because of the way that our brains work with the language as we've learned it. But they mean the same thing from a chemistry standpoint. I believe the second one, maybe it's just that I learned it more recently, but I think that this is the new school where things are going, because it allows, like with the parentheses, it allows you to be more specific.
I love that.
Then use it. Either of these is full credit answer. The other aspect of this that makes things a little bit tricky is that when you have a pi bond, pi bonds can no longer freely rotate because the shape of a pi bond is not symmetric between the two carbons, right? It had that above and below shape. So because our pi bonds, so our sigma bonds are gonna look like this, right? This is where you have good orbital overlap. Pi bonds are always gonna have that above and below shape. It looks kind of like, you can draw it like a kidney bean, or you can draw it like a canoe. But in general, they're gonna look like this, right? Which means you can't, because they have to be sticking straight up and straight down, those unhybridized p orbitals, you can't take this carbon anymore and just rotate it. With the sigma bonds, you could, because they were rotationally symmetric. It didn't matter which way you rotated it, you still had just as much overlap between the orbitals. That's no longer true with a pi bond. So pi bonds, basically, they have a similar naming convention to ring structures, because a ring is another form of what they call a hindered rotation. Hindered just means like you've got in the way of something, right? So if you have a rotation that can't happen anymore, then that means you get locked into various conformers, just like rings. With the ring structures, we looked at cis and trans, right? They're either on the same side of the ring or they're on opposite sides of the ring. We can do the same thing with alkenes. So if we're talking about 2-butene, we need to specify, are they on the same side or are they across the alkene bond? So similar to think about it kind of like the ring structure. And the old school way of doing this was actually to name it with the same terminology, cis and trans. So in which case this would be cis and this one would be trans. But because the chemists like to be totally unambiguous about everything, they decided to give alkenes their own style. And so we use E and Z, which comes from German this time, not Latin, surprisingly. E is for entgegen, which means against. So think like antagonist.
Which is compared to cis and trans, it's just the same as trans.
It's the same as saying trans.
Using like a lowercase e.
Capital E, just like R and S. And we use the same priority system as R and S. So they actually try to make it more similar to R versus S than cis versus trans. We kind of tend to use them interchangeably. So this first one would be E2-butene, or you could say trans-2-butene. When you get a little bit more comfortable with this, I'll talk about that. We do still use trans and entgegen, and they can differ from each other a little bit, but we'll wait till we get a little more comfortable before we bring that in. And then this bottom one is going to be Z2-butene. Z is for, my German spelling is not, I think it's zusammen. Literally just means same. And there might even be another syllable. It might be zusammen or something. Again, my German's not my strong suit. Give me Greek and Latin all day and I can hang, but German and Russian. I was lucky enough last year to have a student who actually grew up speaking Russian.
Well,
And it was actually really helpful because Zaitsev means rabbit in German. And he's the one who had a rival in his same research group, whose name was Markovnikov, and Markovnikov means carrot. So the rabbit ate the carrot because Zaitsev got the last word in their rivalry. And I had never had any clue about that because I don't speak Russian. All right, so these are the IUPAC names, cis and trans.
And we have to put the parentheses around them.
I'm not gonna mark you down if you don't. It is helpful to make sure you at least capitalize them. So I know it wasn't just a typo, but.
So then how do we know which one is gonna be more preferred?
Good, let me clean up some of this. So we can see what's going on. So Zaitsev's rule is you preferentially form the more substituted alkene. So which of these is options is the most substituted?
So the most substituted would mean what exactly?
More carbons around
Okay.
the alkene. Just like more substituted, like tertiary carbon is more substituted than secondary. So more substituted in this case means we're gonna favor these two. So, and then out of these, they're both equally substituted. So what's our next?
Sterics?
So which one would we think would be favored based on sterics? Top one. So that's probably our major product. And really, this is not as strict as our carbocation stability. It's not as big a deal because we're gonna really get a mixture of all three of these products in measurable amounts. Even when we were talking about a tri-substituted alkene versus this version, we didn't see a huge jump between them, right? 2 to 1 basically. Which means if these together make up 60% versus 40%, and then we take that 60% and we split it up into 30%, 35%, and 25%, technically that would make this one the more substitute or the major product. Because if it's 40%, 35%, and 25%. But overall, this 2-butene, the both isomers of the 2-butene combined are the major product. And then if we're really splitting hairs, we'd say, okay, now we're in a gray area because we don't know exactly what these numbers are gonna be. It's gonna be very dependent on the conditions and what the leaving group is and what we started with, et cetera. So I don't expect you to be able to come up with these numbers off the top of your head. If you just went through that same logic we did and circled this one because it's the most substituted, and out of the most substituted, if this one's preferred, that'd be a full credit. I want you to be aware that there is some gray area though. There always is, and that's the thing about OChem is we don't just make the generalizations anymore. All right, how about this molecule here? You want to put it in its skeletal structure. Would look like that.
Does it go to the same carbon in both of those cases then?
You're asking, could we do that too?
No, like for both of those, they're both connected to the
Right,
tertiary.
because the tertiary carbon is where your leaving group was.
Right, so we would only have one arrow going there, but then three different.
So leaving group has to leave from the tertiary carbon. And that means that your hydroxide can come in and grab a hydrogen here. Or here, or here. Alright, so this is why we start getting into skeletal structures and only drawing the hydrogens that matter. The active hydrogens, because it starts looking really crowded otherwise.
One arrow right now, what has to grab.
Well,
So let me clean that up, we'll color code this. So if the hydroxide grabs from that carbon. We're gonna make that product. If our hydroxide grabs from this carbon or this carbon, we get the same product. In either case, those are the same molecule, the green ones.
Okay.
Right, do you see that?
They can't move because they're pi bonds, right?
It can't rotate because they're pi bonds, but you can take the whole molecule and flip it over. So I can't hold these three still and rotate this one, but I can still take the whole molecule and flip it over. And if we were naming these, they're both gonna be butenes. All three of these are butenes. They're both gonna be, they're all gonna be methyl butenes. It's either going to be methyl 2-butene, 2-methyl 2-butene. Or it's going to be 2-methyl 1-butene. Both of these you would name the same way. That's how you know they're the same molecule.
Then what about like our R and S thing?
Do we need an E or a Z on these, on either of these?
No.
Why not?
Because those two are the same, they're not different. So
These two are the same, they're not different. And so just like with chiral carbons, we know whether we need R versus S based on you had to have 4 different things attached to the same carbon, right? For an alkene, you need at least one side of the or both sides of the alkene have to have 2 different things attached to it. Otherwise, if you switch these two, they're both methyls, right?
Yeah.
So if you switched them, we'd get the same thing. And same here with hydrogens. So if we look at the blue one, we've got a methyl and a hydrogen on one side. So obviously we'd know the difference if we switched those two.
Mhm.
But because this is a methyl and that's a methyl. On the other side, if we switch these two, nothing changes. And on this side, we have a hydrogen and a hydrogen. So same thing, you have two identical substituents on one side of the alkene. So you can't tell the difference between a cis and a trans. And so you only need E and Z if you can tell the difference on both sides of the alkene. So on this one, we had ethyl versus a methyl, but on that side, they're both just hydrogens, so we can't tell the difference, so no E and Z.
So just because there's two bonds and two bonds.
Not just two bonds, but they're to the same thing on this side. These two hydrogens are identical, so if we switch them,
Oh.
we wouldn't be able to tell the difference. So those are the easy alkenes to name. You don't even need to worry about E and Z as long as one side of your alkene is symmetrical. Let's look at the last one. Oh, sorry. See if I can, no, I erased him.
Well,
That's okay,
So-
you can redraw them fast.
one would be the most substituted,
Blue is gonna be more substituted.
so that it would be our.
That's our major product.
Well, but the other two are the same, so do we even look at sterics or do we just say that they're the same?
They're the same. So for this last one. Our hydroxide can grab a hydrogen here. Or it can grab the only hydrogen on the tertiary carbon.
Okay.
So this is the same product we just had on the last one. It's tri-substitute, you got three things attached to it, which is almost as substituted as you can be. So that's gonna be 2-methyl, 2-butene. Do we need to worry about an E and a Z? For the green one? And why not?
Well,
Or
I
why?
guess yes, because the last little leg could flip down.
Could flip down. Could we tell the difference on the other side though? We've got to be able to tell the difference on both sides.
Well,
Because these two methyls are the same. No E and Z. And then how about the blue one? Well, how would we name it?
two.
We wanna keep the numbers as low as possible, right?
So would you wanna do 1 or 2? 3-methyl-2-butane.
So you only name one side of the alkene. Because if it has to be between two sequential carbons. So you don't need to say 1,2-butene, because it has to be, if it starts on carbon 1, the other side of it has to be carbon 2.
Why 3-methyl?
Cause then it would be 3 if it goes 1, 2, 3.
If this is carbon 1, 2, 3. Because the alkene group is on this side, we have to start counting over here. It's more important to keep this number low than it is to keep the methyl group low. Basically, whatever you name, whatever's last in the name is most important. And that's the one you want to keep as low as possible.
So then the green one would be more substituted. So
Green one's
we-
more substituted, so that's gonna be the major product. All right, so how do we feel about Zaitsev's rule?
Okay.
At least we have a preference. So it's not just all totally random, right? Even if that is one more variable to keep track of. So let's talk about last thing before we take a break and switch gears. Let's talk about what happens when you get the anti-Zaitsev product. We don't actually call it the anti-Zaitsev product, it's called the Hoffman product. And that's a really common name, it turns out, in organic chemistry. Not because this is a case where it's not all the same person, like Arrhenius was all over the place. He had major discoveries in several different chemistry fields. There's actually just 4 different Hoffmans that all have different spellings.
Okay.
They're all German organic chemists were really huge and foundational in early organic chemistry. So this is 1F, 2Ns. There's also 2Fs, 2Ns, 2Fs, 1N, 1F, 1N. Are all 4, we have 4 different possible ways to spell Hoffman, and they all show up in organic chemistry textbooks. For now, I'm not going to quiz you on which Hoffman is which or anything, don't worry.
Okay.
The Hoffman product is just the opposite of the Zaitsev product. The Zaitsev product is the most substituted product. The Hoffman product is the least substituted product. And basically, this happens just because of sterics. If you pick your base carefully, you can wind up with a good base that has a lot of steric hindrance, has a lot of other junk attached to it that gets in the way. And if that's the case, you can't get in and attack the more substituted carbon. So here's our example, same molecule we saw before. If you use ethoxide as your base, ethoxide is a strong base, it's not sterically hindered because it just has an ethyl attached to an OH. We see mostly the Zaitsev product. The most substituted product gets formed. If we start making the stuff attached to that base bigger, we flip those ratios. And that's just because this big T-butyl group gets in the way so that this hydroxide cannot get in there as well. So what it does instead is it grabs one of the hydrogens from the outside because those are easy to get to. So the Hoffman product is the less substituted product, the Zaitsev product is the more substituted. And we can control that just by using a sterically hindered base. This is the one we see most commonly. That's the one that when I'm writing tests, I typically use as the signal, like this is a sterically hindered base. And we talked about this already. If we get an E or Z option, between those, we can pick which is going to be the major just by looking at sterics. We're going to pick on each side. If there's an E and a Z, that means we can tell the difference between both sides, right? So whatever's largest, you just want to put on opposite sides from each other.
So when we look at E2 reactions, we always look at the Hoffman.
We only look at Hoffman if it's a sterically hindered base. Right, if you get these big, if you have T-bu-OK, it's short for T-butyl ethoxide or T-butoxide, potassium T-butoxide. The K is the potassium. They just to balance the charge.
And how do we know it's a sterically hindered base?
Because it's got a whole bunch of stuff attached to where the oxygen's
Like it'll
attached.
be drawn.
It'll either be drawn or this is the one that I want you to key in on. If you see this one, even if it's just written as T-bu-OK, I want you to think Hoffman product.
But like the one we have for our next one, like the what is this?
Like this one?
The NaOET.
So that's sodium ethoxide. So that's not a sterically hindered base. The OET, ET, remember, is shorthand for ethyl.
Right.
So that is just.
Is the OET the same as in the one before the ETO?
Yeah. We're gonna leave that one for today because I dumped a whole bunch of new details on you all at once. We'll come back and talk about that one on Thursday. We're gonna talk more about these SN1, SN2, E1, E2. That is the rest of this class. And so on Thursday, and then when we come back from Thanksgiving break, that's what we're talking about, is those four mechanisms and really diving into how do you pick which one is most important and how do I get the right products. That's all there is for the rest of this course, for this quarter.
And the essential oil lab is due this week.
It'll be due the end of this week. Just so we clean things up before Thanksgiving.
Right.
I'll give you an assignment over Thanksgiving, but it'll be just some practice drawing products.
Okay.
We'll probably still put it into the quizzes category.
Maybe a little bit longer.
Maybe a little bit, yeah. Most likely, actually, what I'll do is I'll just make the quiz that I didn't give you last week, I'll give you this week. Because we've now added the couple extra wrinkles you hadn't seen yet.
Yeah.
All right, so this aspect, the sterics is actually a good example of why we use E and Z and not just cis and trans. Because if we have a molecule like so if we have this molecule, we could name this molecule. It'd be long, we'd have to, this is a complicated branch, so we'd have to name it with parentheses. But actually, other than that, so 1, 2, 3, 4, 5, 6, 7, so it'd be heptene. Be 2 heptene, and then we would have this 3 dimethyl ethyl.
Was it? No, dimenes 2.
Yes.
Diamines 2. So because our ethyl group has 2 methyls attached to it, we put it in the parentheses. So if we're deciding which of these is more stable, either this version or with the methyl flipped the other way. I'm gonna draw it. One, 2, 5, 6, 7.
They're not the same thing.
No.
Not because this methyl is flipped. So it's E and a Z difference, right? Which of these is going to be favored? Red or the blue?
Well, how do you say which is cis, which is E and which is Z?
Okay, let's do that first. So
Z is cis, which is same, right? And trans is E, which is opposite.
so Z is the same side is the other way. So say it with a bad French accent.
The same.
Z is the same side versus E is opposite, is against, entgegen. So which of these is which? Well, when you are assigning priority for these, you just look at, in this case, it's going to be carbon 2, and you assign priority for the 2 things attached to it. The methyl is going to have a higher priority than a hydrogen. So circle that one. On the other side, which side is the higher priority? The longer chain, because we get carbon and a carbon, so they're tied. We assign priority the same way like with RNS, we do atomic numbers. So carbon and carbon is a tie. Go one step further, carbon and a carbon, it's a tie. Next step is a hydrogen versus another carbon. So this has the higher priority. They're on the same side, so that's Z. Versus on this one, our priority is down and up. So they're on opposite sides, so that's our E.
But really, that didn't we want to look at sterics.
We want to look at sterics though. So this is a case where E versus Z is not as important as what's bigger. So we can't just say it always forms as E. Because this is a case where the chain, the main carbon chain, is not the biggest thing. This T-butyl group the T-butyl group is bigger. So we're going to put that on opposite side from the methyl.
So our major is gonna be the first one, the red one.
Major is gonna be the red one in this case. Alright, and so the last piece that I'm gonna, the last wrinkle that I'm adding before we take our break is that the difference between cis and trans and E versus Z is that cis and trans always refers to the carbon chain. E and Z uses the priority system. So you can have cases where a molecule is trans but Z.
Well, no, so we're looking at this in relation to this, because this is our biggest, this is gonna be our
That's
big
bigger
pusher.
than that.
Yeah, because it's all clumped together. So you're looking at how they're gonna push against that. And with that methyl up there, it's gonna, all of this sterics is gonna be up here, and these sterics are gonna be here. So they're not gonna bump into each other.
But like when assigning priority, it's one.
Exactly. So assigning priority is different than the sterics. Assigning priority, you just look at what's the largest atomic number that's directly attached. And then if they're a tie, you go one step further out.
We've done this before, do you remember doing it?
Yes, I just like. Still kind of confused on how.
Well,
we do
so-
it for these.
We go like, we both start here, right? One out is carbon, one out is carbon. One more out is carbon, one more out is carbon. One more out is carbon here, one more out is hydrogen here. Carbon takes priority.
Right, so this is a what?
So that is the higher priority
For this, like doing.
for deciding E and Z,
Z.
but it's not the biggest in terms of sterics.
Right, but for deciding E and Z, that one's one.
Yes.
And then this one's two and this one's three.
No.
So you don't
This
do,
one's not.
hold on, right? For E and Z, you don't do 1, 2, 3, 4. For E and Z, you do 1 and 2, and then 1 and 2.
Oh, on each side.
Exactly.
No, don't include that.
Yes, include that. Cause you're looking at the two sides.
This is your other side.
You compare your big ones of your two sides?
In general, you want to put your largest things opposite from each other.
But having them on the same side makes them cis.
But so then in terms of priority, you've got both of these, your number one priority is on the same side.
Cause there's nothing down here.
Because it's a hydrogen, but hydrogen's the lowest priority, right? So because you have your highest priority is on the same side, it's Z.
Which is the cis? Yes.
Yeah.
The same side.
This same side. So look at this, let's look at a smaller molecule. This is another one, and I have it drawn completely out. So drawing the complete structure for these when you're first learning how to assign the priority can be helpful because you can see all the different steps you can take. In this case, in the blue side, this is the carbon chain is cis.
Right.
But it's E. Because bromine has priority, even though the carbon chain goes the other way, because bromine has the higher atomic number, it has priority. So this is both cis and E. So that is the one time where you can't just say that cis and E are cis and Z are interchangeable, because you can have cases where that's not the case. All right. Let's take our break. Let's come back at 10 after. We'll talk about NMR.
Question about the lab today.
Yes, I was hoping I was gonna see you.
Yeah,
You wanna go get some dry ice?
dry ice and lemons.
Dry ice
Yeah.
and lemons.
Okay, I'm going to high school anyway because I'm picking up
Cool.
physics equipment. No, I know
Awesome.
where I'm going, so.
Do you know where you're going?
For physics, yes, because I
Okay.
went with Adam last week.
Okay.
It's like, if you wanna do it, just go for it.
Chemistry's the same building, just the other corner.
Okay,
And it looks like a chem lab. They have gas spigots and stuff, so you can always find that one too, but.
okay, yeah, so lemons, and
lemons.
one of them is gonna be doing the cloves still, or everybody's doing?
Either way, would you prefer to work with the
I
lemons
think
today or the clove?
I think clove, I don't know if clove has enough.
If we have enough, why don't you get some more dried cloves too?
I mean, we have enough cloves,
Oh.
I don't know if it has enough oil.
Oh, do
We
not?
always do the lemon.
The lemon gets better, okay,
Always.
then we'll do lemons.
Okay, I would just get lemons and try it. Okey doke.
Perfect, see you in a bit. All right, so let's come back at 10 after. And we'll switch gears.
Okay. Do we know?
Hmm?
Okay, let me go back a moment to an video. Are you okay? Do you need help? Do you get
I
it?
don't understand what we were doing.
Okay. All this is showing is that our carbon chain. Look at me, our carbon chain is cis. Right? Cause the carbons, oh,
I'm gonna kill you.
oh no, did I lose it? I might have lost. Do you have it down?
No,
Okay, yes, you do.
no,
This
I
is
wanted
it.
to draw the other one too.
So the other one is just the carbon up here. And the bromine down there.
And what on the other side?
Carbon, carbon,
No, that one did
Oh,
not have.
carbon, hydrogen. Same thing. Okay. So with this, our carbons are on the same side. They're cis. With this, our carbons are on opposite side, they're trans. However, when we look at priority for Z and E, this one is what?
Well, we're comparing our biggest ones, which is this one and this one.
So
So
it's,
it's trans, so it's E.
so it's E and cis.
Okay. Okay, now I get it. I don't know what we're doing, but let's go do it.
No clue. You all talk about ourselves.
See you later.
Sorry, Renee.
No worries.
Change the thing in the iPad. It's like a QR code, but it's like not working and you have to like ask someone to check you out now and it's really annoying, honestly.
Do you toast your Uncrustables?
Because they're frozen, so I just toast
I
it.
kind of like them frozen.
Sometimes I do too, but I
Okay,
like them
interesting.
crispy.
I can see that.
My teeth are too sensitive.
But the jelly's still cold.
Okay.
Gotta master the toaster.
Huh?
You gotta master the toaster.
All right.
What do you get that?
So let's talk about NMR.
Are these on our slides?
It is. I skipped forward about 5 slides and we're going to add the coplanar and things like that on Thursday. So NMR is, as I mentioned before, it's another way of figuring out what stuff is, what structures are, what it even gets into is your, with a little bit of practice, you can even tell things like, is this cis or trans in terms of alkenes. But the way that it works is a little bit weird because it involves magnetism, and magnetism is tricky. So basically the way NMR spectroscopy works is it looks at, it turns out any nucleus that has a non-integer spin, which basically means an odd number of protons plus neutrons. Turns out protons and neutrons both have their own internal magnetic field because they're each made up of quarks. Neutrons are made up of 2 up quarks and a down quark. Protons are made up of 2 up. One of these is wrong. But regardless, you wind up, they basically, those up and down quarks behave kind of like electrons in that they have spin. And if you have a nucleus that has a non-even number of protons plus neutrons, then that nucleus as a whole has its own magnetic field. So that's anything with a non-even number of nucleons. So most carbons that doesn't apply to, right? Because carbon's most common isotope on Earth is carbon-12, right? So basically we're looking for something with an odd mass number.
They're not a 12.
So not a 12. So carbon-12 will not show up in an NMR. But what will, that's present in almost all of ours? Carbon-13 does show up, and we actually have a whole lecture on carbon-13 next quarter. That's carbon 14, it's a little bit different. Carbon 14 comes from the nitrogen in the upper atmosphere.
In the gen.
And Gen Chem, you
Gen
should have.
Yeah.
But that's been a
We learned
minute.
That 2 years ago.
So this is not a radioactive process though. So we don't need them to go through a radioactive decay like we do for carbon dating. Carbon dating and other types of radioisotope dating, they have to go through a nuclear reaction.
Right.
That's not the case for NMR. And so what are the elements that are most common in organic chemistry besides carbon? Hydrogen. What does hydrogen look like? Hydrogen and oxygen. Most common form of oxygen is oxygen 16.
How do you just know this?
Because he's been doing this a while.
I've been doing this for a while. Think about your molecular weights. Oxygen's molecular weight's really close to 16, right? Hydrogen's most common isotope is 1. That's an odd number. So the first type of NMR that they discovered was proton NMR, was hydrogen NMR. Because every hydrogen atom is going to have its own magnetic field. And what NMR is really looking at is what happens when we align all these magnetic fields and then shine light on it. Right, so, and I should also.
NMR actually mean?
Nuclear magnetic resonance. Which you may notice has 2 similar words. What's MRI stand for?
This machine. You go through it.
Magnetic resonance imaging.
In NMR, they're not nuclear reactions.
Correct. We're looking at the nuclei, but the nuclei are not changing. Nuclear reaction means your nuclei are changing, like carbon 14 turning into carbon 13. Turns out MRI is NMR, but it was first discovered and popularized for medical imaging in the 60s when the word nuclear was a 4-letter word. So they just rebranded.
How was that a 4-letter?
Not literally, figuratively. The word nuclear was very, very scary to people. You told somebody they were going to get a nuclear magnetic resonance done on their body, they would have freaked out in the 60s because they didn't need to know what it was. Nuclear meant bad.
Yeah.
So they just rebranded it and they just removed the word nuclear and added imaging on the end. So MRI is NMR. That's why you need a giant magnet for an MRI. Have either of you gotten an MRI? You have to make sure you have nothing metal, right? You
Yeah.
take out all piercings. It basically, because that giant tube is one huge electromagnet.
Still in this.
You hold really, really still and it's boring, or if you're claustrophobic, it's terrifying.
And it explains.
It spins.
Yeah.
There's
but
a
don't
thing
you,
that
like,
spins around
I
it.
feel like
Isn't it really
buzzing
loud?
more than thinking.
Sherry
Depends on
said
how
it
old
blinked.
Yeah, I
the
don't know.
machine is.
Get when they thought I broke my eye socket,
Oh, that's when.
when I fell off course into an actual fence.
Yeah. So MRI is not usually a good thing for anyone. Like you're not doing great if you have to have an MRI. Yeah, just sit there and
What's the
He
one?
didn't even offer me music. Just
They didn't offer you music? I would
No.
love this.
They're like, it'll take 10 minutes, 30 minutes later. Still sitting.
What's the one where they like flush iodine through your system?
so that's a different type of imaging. But it actually
It's still like,
depends. It can still be the same thing. Sometimes what they do is they take a specific isotope of an element that has an odd number of nucleons so that they can track it through your body. So your standard MRI is mainly just looking at carbons and hydrogens. The same machine, if you change the frequency that it spins at and the strength of the magnetic field, you can actually measure anything else with a odd number of nucleons. So if you take iodine normally, I think
126.9, so
127. So if you want to track where iodine is in the body, then you can just flush extra iodine through and see where it accumulates. They also can do that with basically a Geiger counter as well by actually looking at the radioactivity. If it's something else, so they do that as well sometimes so that it leaves your system in a faster way by basically decaying and going away.
You can track like blood flow and things, and like when I would come home and be like, oh, we like took x-rays of this cat 3 times because we fed it this and looked at it through x-ray to see where the blockage was.
Yes, they do stuff like that too, exactly. That, not all of that, sometimes you can just use a regular x-ray machine if you're using radioactive isotopes to do that. If you use, so they do different approaches depending on what they're trying to track.
We used regular x-ray and
like
they ate
that.
some white paste
Yeah,
thing.
there's a white like liquid that's super thick.
Barium.
That's what it is, and we have to force it down.
Yeah,
Humans take
humans
it
do
too.
it too. So I believe that barium gets used because it doesn't absorb well in the intestinal tract. And so it's a way, if you want to track the intestinal system without worrying about it getting out, you can use barium. So basically, depending on what system in the body you're trying to study, you can basically flush different elements through because like iodine accumulates in the lymph node. So if you're looking at the lymph node, you're going to use iodine contrast. So they do different approaches like that because of the different systems.
Okay.
And that's beyond my pay grade because I don't teach A&P. That's a great
Right.
question for Caroline, the new A&P instructor.
Okay.
What was
What's that?
Like why you would use the different things.
So
we use it
at the molecular level, so basically the medical scale MRI
Yeah.
works the same way. It basically just takes all the information and processes it and turns it into a 3-dimensional image. That's based on where water is in the body mostly, because that's where you're gonna find most of the hydrogens. Since your body is 90% water, every water has 2 hydrogens, you can track where the water is just by looking at where the hydrogens are.
So with our common elements that we use, when we use NMR, we're really only looking at hydrogens.
For now. And again, the medical version of an NMR, I'm less confident talking about, but I believe it's still a proton NMR generally, and that it's looking at the water because that's where the hydrogens are. I could be wrong about that because you can do a carbon NMR. But if you do a carbon NMR, you're just looking at where the carbon 13s are, and there's not as many of them, so you don't get as strong of a signal. The way this works though is basically if you create an exceptionally strong magnetic field, what winds up happening is all of those individual nuclei in your body or in your molecule will spin themselves around because the nuclei are spherical, right? So they can rotate whichever way they want pretty easily. And so if you put them in the presence of a very strong magnetic field, they'll naturally align so that their magnetic field matches the magnetic field that you put them in. And so basically what that does is it creates 2 states. You can have it, they're gonna either be aligned so that they are going parallel to the magnetic field or opposite to the magnetic field. Still parallel, but pointed the opposite direction. And that means that if there's 2 different energy states, that means that we can measure the amount of energy it takes to move from the low energy state to the high energy state by shining light on it.
2 different energy states of the same
Atom. So basically if our magnetic field is going like this, if we have a hydrogen that has its own magnetic field, it can be pointed with the external magnetic field, or it can be pointed opposite of the magnetic field. This is what we call the alpha spin state versus the beta spin state, and that's not that critical right now. But basically all NMR spectroscopy is you take all of these nuclei, you put them in a giant magnetic field so that they all align into this lower energy state. Then you shine light of different frequencies to see where it gets absorbed and bumped to the next level. So it's still spectroscopy in that we're going to shine light on it and see what happens. We're just creating, by putting these things in a super strong magnetic field, we're separating these things into two different states. Normally, if in the absence of a strong magnetic field, all of your hydrogen magnetic fields are all pointed randomly. As soon as you put them in the strong magnetic field, they lock into place, and then you can measure how much energy it takes to go back and forth. That's all NMR is.
You measure.
Basically, you put it in a really dark chamber in that strong magnetic field, and you shine light of different frequencies on it.
We did this in Gen Chem.
We talked about, it's similar to IR spectroscopy and it's similar to UV spectroscopy, where in UV spectroscopy, you're looking at going from your electrons going from one energy state to an empty energy state if you shine light on it.
If you're applied, sorry, I'm gonna let you finish your answer.
So basically we can make stuff glow by shining light on it, and it jumps up in energy level and then it falls back down. That's the same thing we do here, except that this difference in energy is not in the visible region. This is a really small difference in energy, but it's really reliable if the magnetic field is strong enough. So then we basically are just going to scan through a whole bunch of different frequencies, see what gets absorbed and re-emitted. And then that's our signal. That's what we get as when we look at the spectrum from an NMR. Taylor?
If your applied magnetic field is like the arrows go down, is your alpha gonna go point up, or does it point down?
It would point with the magnetic
So
field.
alpha is with and beta is against.
Correct. It's lower energy to go with the magnetic field than to be opposite the magnetic field. But it's always going to be one of those two states, because it turns out being perpendicular to this is even worse. So we can flip back and forth between opposite and with, but we're not going to see really, and that's what that magnetic field does, is it creates these two states. Go ahead.
The carbons that are just floating around.
If it's not carbon-13, then they don't have an odd number of nucleons, which means they don't have a magnetic field and they basically ignore it.
They're just there.
They're just there. They're still in their same molecule. The bonds are still holding everything together.
Is that, like, your hydrogens are attached to your carbons, like how?
So because the hydrogen nuclei are symmetrical, they're just a sphere, they can rotate wherever they want without affecting the orbitals. The electron orbitals are going to keep their same normal shape.
But you just have a whole, like, molecule behind these, just somewhere.
Yeah.
No.
So if I was going to draw, let's just say ethane. We don't usually draw the spheres. We usually just draw the atomic symbols, right? But each of these atoms is a sphere.
Right.
And that's a tiny sphere in the middle of a cloud of electrons. So the magnetic field is going to not affect these two carbons if they're carbon-12s. It's going to only affect the hydrogens because the hydrogens have their own magnetic field. So they can spin around however they want, well, without changing the rest of the structure. And that's where the ball and stick models kind of fall apart. Because it's more like if you can picture building a molecule out of fidget spinners. the nuclei are like the center of the fidget spinners that can spin around freely. You can take the three-sided pieces of it and align those however you want, lock them into position. You can still spin the middle without affecting the rest of what's attached, right?
Yeah.
So the nuclei can rotate independently of the molecule itself because they're just these tiny little spheres.
And each nuclei has
As an arrow.
And each hydrogen nucleus has its own arrow. The carbons don't because they have an even number, an even mass number.
So they have no arrows or they have two arrows?
They have two arrows in opposite directions
So it only works with odd numbers because there's a lone arrow.
because there's a lone arrow. And that's why the electrons don't get affected by it either.
So hydrogens like actually only have one arrow, but then if we were looking at like carbon 13, there's 13 arrows, there's just one more pointing the other way than,
Exactly.
okay.
So carbon 13 is affected by the magnetic field because of that odd number. One of them is unpaired. All really good questions. So in the absence of a magnetic field, all of those different nuclei are just pointed randomly. As soon as you apply the magnetic field, they align either with the magnetic field, which gives you alpha, or against the magnetic field, which gives you beta. And all the NMR is doing is then measuring what's the difference in energy between alpha and beta. Because different atoms in different molecular systems are going to have a different gap in the energy. Not all hydrogens are going to have the same difference in energy between alpha and beta. If it's a hydrogen that's attached to a methyl group that's at the end of a carbon chain, it has a different delta E than a hydrogen that's attached to a tertiary carbon, for instance.
And then you would see them like you get this image like this and you could figure out how your molecule looks.
Exactly. So we don't actually see this. So here's just another graphic. So all of these are just different hydrogens. No magnetic field, they're all random. Turn the magnetic field on, they all align. We shine light that's in the radio region, so really low frequency. So MRIs actually don't contribute. One of the reasons they're preferred over X-rays, they're way more expensive to buy an MRI machine, but they're actually better for you because they only use radio waves. They don't use high energy radiation, so it doesn't contribute to your overall, radiation or carcinogenic or anything like that. So use radio waves and then you wind up putting all of these in the higher energy state. So now they're all in the beta state. And we turn off the light and they're gonna flip back around and give off radio waves when they do it. And the radio waves that they give off get measured. We can just say, okay, we measured one unit of light at this frequency. That means we've got at least one nucleus with this amount of energy between the alpha and beta. And so it winds up looking something like this. This is what an NMR spectrum actually looks like. And this chemical shift down here, that just like with IR, the y-axis is intensity. It's not really useful. Chemical shift is basically related to how much energy it is it between alpha and beta. But it's kind of been processed in a way that we can't actually take it and turn it directly into a photon energy. And so it's presented in these ppm units, parts per million, which don't really mean anything. They're like wave numbers in IR. We use them as a way to kind of categorize, like, oh, we have a signal between 1 and 1.2, therefore we know this. But they're not units that we're ever going to do any math with, really. So the information that we can get from this is a lot less cluttered than an IR spectrum, right?
Yeah, it's much more specific.
Much more specific. And basically where things are from left to right is gonna tell you about how much electron density there is around them. So the closer it is to zero, the more, we call that more shielded it is. Basically, the more electron density it has around it. The hydrogens that have the most electron density around them, they feel the magnetic field a little bit less because they're surrounded by the electrons, and each electron has its own magnetic field. So basically, the further to the right is more electron density. We say more shielded. Versus less shielded. So less shielded means that there's less electron density around it, but it also means that we can look at different functional groups and see approximately where they're going to fit in there, because every different functional group is going to affect its protons a little bit differently. But one of the first thing to look at with these that's kind of, it's almost so obvious that people miss it. It's the number of signals. The number of signals tells you how many hydrogens, how many unique hydrogens you have.
So the signals though, are we talking like 1, 2, 3, or like within that first one we have like
1, 2, 3.
Okay.
So that's a signal. That's a signal. This is blurring the lines a little bit. Usually if it's a nice clean signal, these peaks within the signal kind of have a bell curve shape to them. So like the intensity is like, okay, it's smallest on the outside, biggest in the middle. If that's how you can tell that that's one signal, this doesn't have that shape.
Yeah.
So that tells us that there's more than one proton mixed in at the same spot there. Right, so, but at the very least, we can look at this and say, okay, well, we have one type of proton, two types of protons, and then the fact that this shows up right around 7 is its own really obvious hint. Because benzene hydrogens, aromatic hydrogens, always show up between about 6.5 and 7.5. And I have a table just like with the IR that says, look at this, you know, if you see a peak in this area, it's probably that. But with a little bit of practice, you can start to look at this and say, okay, well, I don't know how many different protons there are, but the fact that it showed up around 7 means I know that there's a benzene ring.
It's between 6 and 7 or 7 and
6.5 and 7.5, I believe. It's always in the same. All your alkenes or alkanes show up down below 4. Your aldehydes show up, and carboxylic acids show up way past 10. The only thing that really shows up in that 7 region is aromatics. So just like with IR, there were a couple of key things to look at. Without even getting into the more information here, this makes it crystal clear right off the bat, I have a benzene ring. I don't even need to know what the formula is for this compound or have an IR, because there's only 3 signals and they're so clean, and where they show up means I can tell you exactly what molecule that is. Granted, I made the slide, so I should be able to, but I haven't looked at these in a year. And I can still tell you exactly what that molecule is.
Would this be a benzene ring with 2 methyl groups?
Close. That's exactly the right approach. It's a benzene ring with 2 other types of hydrogens.
But what, they're different sizes, so like one's got to be a methyl and one's got to be an ethyl or something.
an methyl and an ethyl, but remember, it's the different hydrogens on that group. So if we had an ethyl group, and remember, we're looking at the hydrogens. So you're exactly right, Taylor, it is ethyl benzene. Because we've got 5 hydrogens that are part of the benzene ring that are all showing up over here. Then we have 2 other types of hydrogens. There's a total of 5 hydrogens, but there's 2 other types of hydrogens. There's the secondary carbon hydrogen, and then there's the primary carbon hydrogens. That's why there's 2 signals here. And how we can tell which is which, or that it looks like this and not 2 methyl groups. One, if it was 2 methyl groups, they'd be identical to each other. Right? Because no matter where I put the other methyl group here, it's identical to the other one. So those would show up as the same signal then.
In different locations.
No,
It's
they'd
like
be
layers.
on top of each other to the point where you couldn't tell them apart. It's like all of 3 of these are showing up as one signal. And both of these are showing up as one signal. Not on top of each other, but literally the same signal because they're identical.
And then because the ones on the ring are identical, they show up.
But why not on top of each other?
So these 2 are identical to each other, and these 2 are identical to each other, and that one's not identical to anything. So that's why we have a mess over here, is it's really 3 signals on top of each other.
Wouldn't those ones be on top of each other?
Because we literally can't tell the difference between this hydrogen and that hydrogen. These ones, we could say, okay, well, these 2 hydrogens are both 1 carbon away from the ethyl group, so they're identical. These 2 hydrogens are both 2 carbons away from the ethyl group, so they're identical. But we can't tell the difference between these 2. We can tell the difference between these 2 and that one.
But wouldn't you still get 2 signals from the 2 identical ones?
Turns out you don't. Because they are symmetric and we can't tell the difference between them, they show up all as one signal. They have exactly the same energies. So that's actually where the intensity comes to play, because it turns out how big these peaks are is based on how many hydrogens are part of that signal. And that's number 3 on here. So we'll get there in this. So I guess now's the perfect time to talk about that. The area under each signal. So it's not just how high it is, it's the integral. So think back to when we did the GC and we had to add up all the rectangles. The integral of these signals is proportional to the number of hydrogens. So if we found the integral, and we basically just use a computer program to do that, to add that up. And you basically say, okay, add up everything between here and here. And then between here and here, and between here and here.
Is there a Green's calculator?
I'm sure it could. This is not a differentiable or a differentiable function. So because it's not a clean mathematical function, there is no mathematical function for this shape. So that's why we'd have to go to approach like we did for the GC, where we'd like make a whole bunch of rectangles.
Yeah.
Used on that, on the GC lab of how to make
I'm
the.
still not sure I did it 100% correct, but
Let's talk about that in lab today. We'll have some time. The way that we show this, the integration, when we do this, is we basically make like an integral sign. It just looks kind of like that. And the height of that sign is proportional to how many hydrogens are in that signal.
people in really big physics class use that.
Yes.
An S.
That's supposed to look like an S.
But like a flat S, right?
So basically, to know how many hydrogens are in there, we just say, okay, whatever your smallest S is, call that 1. And then everything else is gonna be relative to that. So if that's a 1, this is a 1.5, this is a 2.5. We can't actually have 1.5 and 2.5 though, for number of hydrogens though, right? So if we're looking at these relative to each other, if we can't have 1.5 and 2.5, what do we actually have to have? 2 and 3 and what does the 2.5 become?
Oh, 1 and 2. What?
So if that's a 2, that becomes a 3, we just doubled everything, right? What's double 2.5? So basically this tells you how many hydrogens are in each of these signals. So NMR is really powerful, but it can be overwhelming how much information there is. So like I said, because I've been doing this long enough, I can look at this and say, oh, I know it's ethylbenzene pretty quickly. But that's because I'm looking at all 4 of these things kind of simultaneously. The last one we didn't even talk about yet. And the last one is also really useful. So the number 3 tells you how many protons are in each signal. Number 4 tells you how many neighboring protons you have. The number of peaks within the signal, like this looks like this is 3 peaks on top of each other, right?
Yeah.
Or sorry, it's one signal split into 3 peaks. We call that a triplet. Which would make this a quartet, not a quadruplet. A triplet means that it follows what's called the n+1 rule, then where n is the number of adjacent hydrogens. If there are 2 adjacent hydrogens, it shows up as a triplet. If there are 3 adjacent hydrogens, it shows up as a quartet. If there are no adjacent hydrogens, it just shows up as a single peak.
Which would just be a random hydrogen floating around.
Like if we just had something that looked like this,
Yeah.
no splitting, call this splitting.
Right.
If there's no splitting, then that just means there's no adjacent hydrogens. It can also mean that it's an OH hydrogen, because when you have an oxygen, when it's attached to an oxygen instead of a carbon, you don't get the peak splitting as much. But that's splitting hairs, not peaks. All right, so the rest of these slides start talking about, so the other term is, so more de-shielded is that way. More shielded is upfield. Is the other term that's used. I use shielded and de-shielded. I don't use upfield and downfield as much, but so you've seen them before. And I also don't know why it's always presented with 0 over here and counting from right to left. That's a very good question. It seems like that'd be a really obvious thing to do, since we're used to thinking from left to right. We don't. I've never seen, I've read a lot of OChem textbooks. I've never seen one that counted the other way.
So we don't just cause, or we don't for a reason?
If there's a reason, I don't know it.
Okay.
I'm sure that there's a historical reason, and it probably just got precedent was set that you do it this way, and then nobody's ever changed it, because it's really hard to get people to change about anything.
Yep.
But I don't know that for certain. So here's an example of a table, sometimes they're presented as a table. This is clearly from compound chemistry. You can tell by the style.
Yeah.
Again, counting 0 over here. This TMS basically gets used as a marker for 0. It stands for tetramethylsilane. It's a common solvent that organic molecules dissolve in. You don't need to know much. So it's a silicon with 4 methyls around it. And basically those hydrogens then are really shielded. So it's basically what we set as 0. It's just by convention. 0 is always where you see your TMS signal. Because no organic compound will ever have any hydrogens show up to the right of that. So we just use that as a convenient 0. More downfield means more deshielded. So basically anything where you've got a whole bunch of electrons withdrawing, things that are electronegative, resonance, things like that, move things off to the left. So this one in particular, there's our aromatic. It says starting from 6 to 8.5, you can find stuff in there. Anything you see, and there's really not a whole lot else that shows up right there. So that's why it's a really convenient thing to look for. Like, we couldn't tell from the IR very clearly if we had benzene rings, right? We could guess based on the formula. This makes it really crystal clear. Boom, something aromatic. And then you've got all these other ones on top of each other. Primary alkyls, secondary alkyls, tertiary alkyls, allylic, meaning one away from an alkene. All of these kind of show up on top of each other a little bit. So the shielding is a little bit less useful for determining those. And that's where we start looking at splitting and the integration, the size of the peaks. Right, so we're at time right now. You guys have club today? You have Senate? All right, then I'm not gonna go over. We'll just finish, we'll let that digest a little bit and we'll come back to that and we'll do a little mini lecture at the beginning of lab.
Okay.
So